Hi guys. So here we are with our 3B notes. So this is like still our 8.1. This is an intro to unit 8, which is exponential functions. And just like we did with every single unit so far this year, we've always talked about what the parent function looks like and how to transform it. And remember, those transformations did not change. How do we, represent the shift right, shift left, up, down, vertical stretches and compressions, horizontal stretches and compressions? They all look the same. So based on your 3A notes, your video from Tuesday, you should know what the typical growth and decay look like for exponential functions. Okay, so here we are with our exponential parent function. We're going to be using a base of greater than 1. So that is going to be showing a growth. This pattern that I'm going to show you, though, is going to be able to be applied for a base that's less than 1 but bigger than 0 to show decay as well. Okay, so if our base is greater than 1, we know we're showing growth. For our x values, I'm going to be using -2, -1, 0, 1, and 2, just like we always do. 0 is going to be really easy because if I'm using some base, some number raised to the x power, anything raised to the 0 power is going to give us 1. That means the point 0, 1 will always be on our graph unless it's transformed by some vertical stretch or compression or has been reflected. Okay, but the point 0, 1 is always a good point to use. If I use 1 as my x value, anything raised to the first power is just that number. It's going to be whatever our base is. I don't know what my base is here, but let's say my base is 2. Well, 2 to the first power is just 2. Let's say my base is 10. 10 to the first power is 10. Okay, whatever your base is raised to the first power will just be that number. Typically, your bases that we use, you're going to see a lot of 2s as a base, 10 as a base, E as a base. Remember, we talked about what E is. It's approximately that 2.718. It's that irrational number. Those kinds of things. And then, of course, if 2 is my x value, any number raised to the second power is just that number squared. So it's whatever my base is squared. If -1 is my exponent, you know by now that raising a number to a negative exponent is going to create that reciprocal. So if a -1 is my x value, then this is going to be 1 over whatever my base is. And if -2 is my exponent, then that's going to be 1 over whatever my base is squared. So these give us some really good points to plot on our graph. They're not going to be easy to plot because sometimes you're going to get some nasty fractions like 1/8 or 3/4 or whatever, but it gives us a good idea of what that graph will look like. Okay. So if I'm choosing a base that is bigger than 1, let's say I pick 2 or 10 or whatever, then with these points, I know that I'd have 0, 1, 1 comma whatever my base is, 2 comma whatever my base is squared. -1 would be 1 over that base. -2 be getting closer and closer to that horizontal asymptote we talked about, y equals 0. Okay. So let's talk about some of those characteristics, domain, range, all those different intervals we've talked about. The domain of this exponential function is going to be from -infinity all the way to infinity. And I want you to think about, for any exponential function, is it going to be -infinity to positive infinity? What if I showed you something like decay on a graph? Would that still have a domain of -infinity to positive infinity? Absolutely, yes. Okay, no matter what kind of exponential function you have, no matter how it's been transformed, you're gonna have a domain of -infinity to positive infinity, always. Okay, our range here, remember range is those y values from bottom to top. Our lowest y value is going to be 0. Remember, we're getting closer and closer and closer to 0, but we're never going to have a value of 0. That means we cannot use a bracket here, so we use a parenthesis, 0, and then it goes all the way up to infinity. That range is going to be based on where your horizontal asymptote is. So if we were to shift this graph up or down, that's going to affect that horizontal asymptote, so that will affect my range. Also, if I were to reflect it over that x-axis, that would affect my range as well. Okay, for this particular problem, because my base is bigger than 1, it's showing that growth. Where is this function increasing? Well, it's increasing the whole time. Negative infinity to positive infinity, which means it's decreasing never. Okay, where's this graph positive? Well, it's positive from positive from negative infinity to positive infinity. Where is it negative? Never. Remember, positive and negative is above the x-axis or below the x-axis. This whole entire graph is above the x-axis, so it's all positive. There is nowhere where it's negative. Symmetry, it doesn't have any. Asymptotes, we know it has that one horizontal asymptote at y equals 0. These exponential functions will always have a horizontal asymptote. If it hasn't been shifted up or down, then it's going to be at y equals 0. And then, of course, in behavior. Remember, in behavior, as x approaches infinity or as x approaches negative infinity, where does our y values approach? Well, as x's are approaching infinity, as my x's are getting bigger, my y values are also approaching infinity. As x's are approaching negative infinity, they're going to the left, then they are approaching 0. They're not going to negative infinity because they're getting closer and closer and closer to 0 without ever touching or crossing that x-axis. Okay, so here we have this chart that you've seen now 7 times this year. It's been on every single unit set of notes, and you should know by now exactly what to have filled in for the description. Notice that it's already filled in for you. What my main concern is what does that look like for an exponential equation? Okay, so remember, our exponential function is always going to be some base raised to the x power. So instead of a lowercase b for base, I'm going to use a capital B for base, because a lowercase b, we typically use that to denote the horizontal stretches or compressions, right? That's what you see right here. So I don't want to get confused with the horizontal stretch and compression and then what our base is. Because our x is in the exponent, that's where our horizontal stretches and compressions and shifts left and right, that's where they live. Anything vertical is out of that exponent. It's going to be in front or it's going to be behind. Okay, think of it like your exponent is that set of parentheses. Remember, anything that was inside of those parentheses was a horizontal shift or a horizontal stretch or compression. Anything outside the parentheses was a vertical stretch or compression or shift up and down. Same thing here, it's just that those parentheses are our exponent. So if it's in the exponent, it's a horizontal transformation. If it's not in the exponent, it's a vertical transformation. So how do we denote shifting right or left? Well, that would be whatever our base is raised to the x plus or minus some number. Well, if I'm shifting right, that would be x minus some number. And if I'm shifting left, that would be x plus some number. I know this is really small. Okay. If we have a b value, that's that lowercase b value, that horizontal stretch or compression, we know that it's going to be up in the top. So it's going to be some number times our x. If that number is greater than 1, you know it's a horizontal compression. If that number is less than 1 but bigger than 0, you know that it's a horizontal stretch. And then, of course, if we see that negative with our x in the exponent, so b to the negative x, that is going to be a reflection over the y-axis. All of our vertical transformations are not in the exponent. So if I'm shifting up or down, you know that you're just going to see that outside. So that would be some base raised to the x power and then plus some number, or b some base raised to the x power minus some number. That's our shifts up and our shifts down. If we have a vertical stretch or compression, we're going to see that as that a value, that initial value. Remember, I talked about in this in the Tuesday's notes. A times some base to the x power. You cannot multiply that a and that base together. That a is our vertical stretch or compression, depending on the value of the number. B is the base. That's the number that's being raised to some power. If we want to reflect over the x-axis, then we'll simply put our negative, whatever the base is, raised to the x power. Remember, that is something completely different than this. a negative base raised to an x power, that's not an exponential function. We talked about how that'd be going up and down and up and down and up and down and have holes in the graph. That's not an exponential. Okay, so this is showing some base being raised to an x power, then being applied with that negative out in front to reflect over the x-axis. That's going to change the range like I talked about earlier. Okay, so remember, I'm using capital B here just for our base because the lowercase b technically always represented our horizontal stretches and compressions. Now, if you remember, anytime we talked about transformations, we talked about a pattern, right? When we talked about quadratics, it was right 1 up 1, right 2 up 4, right 3 up 9, etc., etc. And our transformations affected that pattern. Well, we're not going to have one set pattern for exponentials because our base could be any number. It could be 2, it could be e, it could be 10, it could be 3/4, whatever. So there's no one set pattern. However, we do know that the point 0, 1 is always on that graph, right? Anything raised to the 0 power is going to give us a result of 1. Now, that's good news for us, but it's a little bit different of what we've been doing. Whenever we shift left or right or up or down, we typically always put a point there because in all of our other parent functions, we had a point or a point of inflection, a vertex point, something at 0, 0. Well, if I shift up, down, left, right, I would just have placed that new point wherever that transformation took us. Well, the difference here is that we don't have a point at 0, 0. We have the point at 0, 1. And if we have some kind of stretches or compressions, that's going to affect that number. So we can't just shift that point 0, 1 left, right, up, down because of our vertical stretches and compressions and our horizontal stretches and compressions. So what we're going to do for exponentials is we're going to shift the center of the asymptote, or basically we're just shifting our origin. Okay, so if I have some transformations left, right, or up or down, I'm going to move those different ways and I'm going to change it to where my new origin is. And then from that point, I will then go 0, 1 or whatever the case may be. Okay, it's going to make a little bit more sense once we actually get into working some problems out. Before we start graphing, I just want to make sure that we can determine what our base is and what our transformations are from this parent function, and then write down the domain and the range. So in example 1, part A, we have y equals 7 raised to the x plus 1 power. What is your base? What is being raised to a power? 7. That is not the a value. That is not a vertical stretch or compression. Okay, our base here is 7. What are the transformations? Well, the only thing I see happening is an x plus 1 in my exponent, so that means I've shifted left 1 unit. Well, if I just shift left 1 unit, that means my domain is still going to be negative infinity to positive infinity because every single exponential function has that domain. And my range hasn't changed. I still have that horizontal asymptote at 0, and so I know my range is going to be from 0 to infinity. I just shifted left 1 unit. That doesn't affect my up and down, my y values, okay? Going to part B, who's your base? E. E is the base. 3 is our a value. That is representing a vertical stretch. E is what's being raised to some exponent. So transformations, we've already said, 3 is there. That's a vertical stretch. We also see that -5 out behind the exponent. It is not in the exponent. That is shifting down 5. Domain, negative infinity to positive infinity. That will be very easy for you guys for this whole entire unit. That for exponential functions, the domain will always be negative infinity to positive infinity. Our range. Our range has been affected here because we've shifted down 5 units. So our horizontal asymptote has shifted down 5 units. So my lowest y value is -5, not being included, and then still going all the way up to infinity. Okay, because that is a growth. E is greater than 1. Remember, E is approximately 2.718. In our third problem, our base is 3/4. Our transformations. Well, I see it's being raised to the 4x power. So that means it has a horizontal compression. and I see a positive 1. So it's being shifted up 1 unit. Up 1. What's my domain? Negative infinity to positive infinity. And then what's my range? It's been shifted up 1 unit, so horizontal asymptote at 1, and then it's still going to infinity. Even though this is showing decay, okay? Still positive. It hasn't been reflected over that x-axis, okay? So now let's go ahead and start sketching. Again, I'd like to denote who is my base, list out those transformations, and then kind of make a table of what points I'm going to use on this graph. Okay, so here we go. Let me zoom in here. Remember, we said our base cannot be a negative number. So when we see this -2 here being raised to the x plus 3, there's no parentheses. Oops, there's no parentheses saying that's -2 raised to a power. That is just -2 raised to the x plus 3 power. So that negative in front is telling me, hey, you're reflecting over the x-axis, excuse me. My base is 2. Base is 2. X plus 3 as the exponent means that I've shifted left 3. And then that -1 behind means I went down 1. So what I can do right now is I can take care of that shift left 3 and down 1 by moving the origin of this graph. So left 3, down 1, I'm going to go ahead and just place an X there because I know that's not a point on my graph, but everything has been shifted now left 3, down 1. So I also know that my horizontal asymptote is at y equals -1. Now, for my parent function, it was always 0, 1, 1, the base, and our base here is 2, and then -1, 1 over the base. Well, that would be 1 over 2 in our case. If you're capable of doing some more points, you are definitely more than welcome to do that. This would be an easy problem where you could do exponent of 2, what's 2 to the second power? Well, that would just be 4. Okay, that would be easy to graph. But before I plot these points, I need to take into consideration the other transformations that have been applied. We are doing everything from this point, -3, -1, right? So we're not plotting 0, 1 right here. We would be plotting 0, 1 from our new origin, which would be right here, okay? I'm not going to do that just yet because I have other transformations that have been applied. So let me go ahead and change colors and show you. If I reflect over the x-axis, that means I'm making all my y values negative. So really going boom, 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 boom. Now I can plot these points. From my new origin, from that point, -3, -1, I can go 0, left and right, down 1. So that would be here. I could go right 1, down 2, which would be here. I could go left 1, down 1/2, right here. I could also go right 2, down 4, which would be here. And now I can kind of connect my dots and see my exponential function. Okay. And I like to always go back and kind of ask myself, what would this have looked like if it was just 2 to the x power? Now, shift it left, shift it down, reflect it. Am I seeing my blue graph? Absolutely. Okay, I also want to list out the domain and the range. Domain, as we said, is always going to be from -infinity to positive infinity. Range here. Two things have affected our range. We've been reflected over the x-axis and we shifted down 1. Those are things that affect the range, shifting up or down and reflecting over the x-axis. So from bottom to top, our range, our y values, would be from -infinity all the way up to -1. Because that's where that horizontal asymptote is now. It's getting closer and closer and closer to -1. Let's go ahead and try part B. So again, I like to denote who is my base, what are the transformations, and then try to get those points to plot it on the graph. Well, my base here is E. And remember, E is approximately 2.718. So that's going to help us in plotting these points. There's no way that we can be very, very accurate here, but we can estimate that E is between 2 and 3, closer to 3. Okay, so that's our base. Well, when I go to list my transformations, I notice that my exponent is 1/2 x minus 3. And I'm hoping that a red flag is going off in your brain right now because you knew that anytime you have a B value, a horizontal stretch or compression, what do you have to do? You have to factor it out. Remember, I told you, if you look inside those parentheses and there's something in front of the x, you have to factor it out. Well, we don't have a set of parentheses here, but anything inside of the exponent, anything that's listed in the exponent, if there's a number in front of the x, you need to factor it out because that affects your shifting left and shifting right and how much, okay? So I'm going to rewrite this as e to the 1/2 open parentheses. This is now x minus 6 and then plus 1. If I distribute that 1/2, I would get 1/2 x minus 3. Okay, so I haven't changed anything, I just rewrote it. So now I can list my transformations as a horizontal stretch, because I had that 1/2. I'm going right 6 and up 1. Okay, so I'm going to go ahead and move my origin right 6 up 1. So right 6 up 1, my new origin is right here, which means my new horizontal asymptote is y equals 1. That's going to affect our range, okay? So from the point 6 comma 1, our parent function said you're always going to go 0, 1, 1, the base. Well, the base here is e, so I'm just going to put 2.7 because there's no way we can put, be exact on that. So 2.7 is good enough. You could go ahead and fit 2, and then I'll talk about -1 as well. 2 is always going to be our base squared. So you could go ahead and grab a calculator right now and put 2.7 squared, or you can even put e squared, but that's going to give you about 7.3. And then -1, remember that's 1 over e. So that's 1 over that 2.7, which is approximately 0.37. Really hard to graph, guys. Okay, so 3 points is good enough. If you can fit 4 or more, that's going to give you a better representation of that graph. But you always want to choose 0 and 1, 1 in the base, and then -1 and 1 over the base, that reciprocal. If you can fit the 2 or the -2, that'll just help give you a better idea of that graph. Okay, now I can't plot these points just yet because there's been other transformations that have been applied. I've already taken care of the right 6 up 1 because that's my new origin. That's giving me that new horizontal asymptote, but I also need to apply that horizontal stretch. That horizontal stretch is going to affect our x values. So I need to go through and multiply my x values by 2. Remember, I saw a 1/2 there, but you're dividing by that 1/2, which is the same thing as multiplying by 2. So 0 times 2 is still 0. 1 times 2 is 2. This will be 4, and then this will be -2. So now from our new origin, 6 comma 1, I can go left or right nothing, up 1. So that'll be here. I can go right 2 and up 2.7. So right 2 up 2.7 would be about right here. I could go right 4. I know I'll go off the graph a little bit, but I can show you that. Going right 4 and then going up 7.3. So it'd be 1, 2, 3, 4, 5, 6, 7.3. Would be somewhere about right here. And then if I go left 2 from my new origin, I'm only going up 0.37. So really close to that horizontal asymptote right there. And then that'll show me my exponential function. Listing out our domain and range. Domain, as you know, will always be from -infinity to positive infinity. Our range now, like I said, has been affected by that shift up. Our new horizontal asymptote is y equals 1. So from bottom to top, what are those y values? 1 to infinity. So what affects the range is any shifts up or down and any reflections over that x-axis. So this will be a good point if you want to pause and try to do C and D by yourself. Identify the base, list out the transformations, write the parent function, transform it as you need, and then sketch a graph. So I'll go ahead and work these out right here. So in this problem, what is our base? Our base is 4. Okay, and so now I need to list out my transformations. Well, the first thing I see is a negative, so that means I've been reflecting over the x-axis. The second thing I see is a 1/2, so that is a vertical compression. Then I see a negative in my exponent, so that means I've reflected over the y-axis. And then I see that +2, so that means I've gone up 2 units. Seems like a lot of things are going on. First things first, take into account your shifts, up, down, left, and right. I've only shifted up 2 units. So I know that my new origin is now at this point. So I have that new horizontal asymptote at y equals 2. So everything is going to be coming from the point 0, 2. Okay, I'm going to list out my parent function rules, and that would be 0, 1, 1 comma the base, -1, 1 over the base. And then I can go ahead and here and do 2 as well. So that would be the base squared, which we know is 16, because I have a vertical compression. So I know that I'm not really going to go up 16. I'm going to go half of that. Okay, so I've already taken into account the transformation of shifting up 2. Now to this parent function, the 0, 1, 1, 4, -1, 1, 4, I'm going to apply the reflection over the x-axis, the vertical compression, and the reflection over the y-axis. Okay, if I were to reflect over the x-axis, and I'll change colors, if I were to reflect over the x-axis, then that means all of my y values are going to change from positive to negative or negative to positive, right? So that means this is now negative, 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 negative. Okay. If I have that vertical compression of a half, then that means all of them get multiplied by 1/2. So this is actually now really -1/2, -2, -1/8, and then this would just be -8. Okay, so I've taken care of this, I've taken care of that, I've already taken care of that. Now the last thing I need to do is reflect over the y-axis, which would change those x values from positive to negative or negative to positive. 0 doesn't change. This is now -1, +1, and -2. So from my point 0, 2, I'm going to go down 1/2. I'm going to go left 1, down 2. I'm going to go right 1, down 1/8, so really hard to plot, okay? And then I can also go left 2, down 8. So left 1, 2, down 8, 2, 4, 6, 8. And then I can draw my exponential function. Identifying domain and range. Always negative infinity to positive infinity. Range, so think about what affects range. Any kind of shift up or down, which we had, and any kind of reflection over the x-axis, which we had. Okay, so now our y values from bottom to top are negative infinity all the way up to +2, not including 2. Okay, and then the last problem. Identify the base, okay, and then list out those transformations. First thing I see is a 3, so that means I have a vertical stretch. Okay. In my exponent, I see x minus 2, so that means I went right 2 units. And then I see a -4, so I went down 4 units. And there we go. So based on that information, I can shift right 2, down 4, and make my new origin. So right 2, down 4 means my new origin is here, which means my new horizontal asymptote is y equals -4. Okay, so I've already taken care of the right 2, down 4. So from that point to -4, I'm going to use my parent function, 0, 1, 1 the base, -1, 1 over the base. Well, 1 over 1/2 is just 2. Okay. I'm also going to incorporate, let's say, -2. -2 would give me a 4. Okay, and you don't have to add that in, but I'm trying to think about where can I plot another good point to get a good visual of this graph, make it a little bit more accurate, okay? Before I plot these points, I have another transformation that I need to apply, and that's a vertical stretch of 3. A vertical stretch of 3 means all my y values are going to get multiplied by 3. So if I change colors, this is now going to be a 3. This is now going to be a 3/2. This is now going to be a 6. And this is now going to be a 12. And so now I can plot those points from my new origin. So from the point to -4, I can go up 3, 1, 2, 3. I can go right 1, up 1.5. I can go left 1, up 6, 1, 2, 3, 4, 5, 6. And I can go right 2, up 12. Almost off the graph, but we made it, okay? So, connecting the dots, there's my exponential. Makes sense that it's showing decay because my base is a number less than 1 but bigger than 0. It looks like it's been vertically stretched. It looks like it's been shifted right 2, down 4. Domain and range. Range. So it's been shifted down 4, no reflections. So from -4 all the way to infinity. And there you have it. Okay, your practice is only 4 problems, so make sure you identify the base, list out the transformations, write the parent function, transform it as necessary, and then graph those points. I might ask you to, write domain, range, and behavior, whatever. But that's it. If you have any questions, let me know. Bye.